would not subscribe to the things that I've been seeing this morning, which are in the realm of old materialism. And I'm interested in matter as the site for turning actions into consequences. The platform through which we do that, associated with work, is technology. And really the question for me is, how do we physically, in the material realm, bring about the actions associated with our thoughts and dreams and ideals and aspirations? And so in this talk, really, what I want to do is get us up to date on the theory of matter from a scientific perspective right now, and position that within a realm of change itself within science, because as you'll know, between the beginning of the 20th and the 21st century, big revolution itself happened in physics, which was quantum physics. And as Albert Einstein said, quantum physics changes everything except how we do things. And so it's really to kind of try to position this conference's theme of change within a materially changed realm, as according to the insights of quantum physics, the systems theories that have come out of the 20th century, and really think, and also with the age of biology emerging at in the 21st century. No longer is physics and engineering the platform for technology, but science is talking about the biological sciences as the platform for change, as the platform for technology and for the production of work as we enter this new millennium. So there's going to be a bit of science in here, but it's really only to orient. I'd like to bring that up against developments in new technologies. I am an EIC ambassador, so European Innovation Council ambassador, and I have a project with the EIC at the moment. So also there is a kind of a European-wide interest in bringing biology and these biosciences to the table to think about, particularly at a time of crisis for the climate, as to how we might also bring about mediated change. So let me get a handle on handling a PC, because being in the arts, I work with a Mac. So change is inevitable. And as we try to resist its negative impacts, we can, however, make better use of this inevitable drive for material transformation. And in this talk specifically, I want to introduce the concept of metabolic design that enables us to understand and sculpt its dynamic processes. So this is no longer about centralized control. This is about negotiating with matter, not purely as an attitude, but actually as a material platform through which we can start to learn how we can better affect change. And that requires us to recognize the agency of matter. So at first I want to just discuss the fundamental material principles that characterize this engaged idea of change. And also I will give some ideas about how we might start to work with this, not just purely as theory, but maybe the first steps towards a platform for implementation. And I think also that the talks that I've been to today really are still very anthropocentric. And I agree with Jane Bennett on the principle that we cannot completely extract the human out of the equations, but maybe there is an opportunity to have softer power, transformation of power, a cosmopolitics. How do we actually start to imagine and make that part of our living world? So the crisis that we are facing really is an ecosystemic one. So as we're seeing global deterioration and declines in biodiversity, the weather exchanges are becoming more extreme. And I think really we need a new mythos of matter for the 21st century, as Einstein has kind of tried to provoke us to do, so that we can generate new imaginaries for design and innovation as ways of implementing, as ways of engaging, as ways of inviting new relationships that could lead potentially to more vibrant forms of human development. And I think that is the thing that is at stake. And as people settle the planet, one would hope, I would hope, that it would lead to its enlivening rather than its deterioration. I think up until this point, the way that we have implemented human consciousness, desire, and social relations right now has led to this unraveling of nature. And we have weakened nature to a point where we're starting to feel a kind of a material shift, which we might call climate change. So this exploration of a mythos of matter is really also an appreciation of the remarkable conditions, material conditions that make this living planet. And I think that through a different mythos, we can start to reorder our thinking, our relations, and start to cultivate a sense of connection and belonging within a larger cosmos. And this cosmopolitical perspective, I think, allows us a better engagement with the common world, but it requires us to have an expanded view of materiality than is common as our legacy from the Enlightenment. And I think with this, the material realm, which is now familiar, will once again become strange, and the age of discovery begins anew. So I guess the cultural framework in which my work is situated considers Bruno Latour's contemporary rereading of Gaia, invoking this time-honoured troublemaker as the first of the ancient gods to emerge from chaos, and as the agent that recounts our living world as a primal disruptive force. Latour rejects any notions of spiritual unity associated with New Age belief or stable equilibria that govern the world's dynamics as proposed by the scientists like James Lovelock and Lynn Margulis. Latour instead sets the scene for a material-centered, non-human narrative of our world, or more than human. So this geohistorical view is considered a tapestry of interlocking bodies, forces, and flows that are woven together by the actions of tectonic plates, meteorite impacts, and ice ages. In other words, a living entity without humans as yet. Let me just try and PC problems. Click left. There we go. Okay, so I think most of us will probably consider the matter around us, and certainly from the field of architecture, the matter around us is considered to be rather dull and inert. It's divided into blocks. It is actually dictated by the geometries that we impose on it. It's really an illusion that we have carefully constructed through the traditions of modernity, essentially. And instead, I would say that our material world is actually thermodynamically extraordinary. And it's best understood, I think, by considering the energy invested in making our planet an environment, and the tension that they continue to be held in is achieved through this thermodynamically active flow, which resists so far the decay towards equilibrium. And to do that, it's made investments in active processes. So our world's materiality has always been lively. It was never inert. And it's forged from a spinning disk of gas and dust around the young sun that started round about 4.6 billion years ago. So within the cosmos, it's actually a relatively new material entity itself. The importance of this, I think, really is to think about how the events that have shaped the modern world have already been framed by a certain condition of inertia with which we have we don't really have the language and therefore the technological platforms and the imaginaries to really engage and deal with in a convincing way. Next, okay, I'll go up to next then. I don't know, because I keep left clicking, sorry. So around 4.5 billion years ago, Earth collided with a sister planet called Theia. Let me go back, we're not there yet. Okay, no, sorry. I'm going to do thermodynamics first, yeah. Sorry, I'm going to talk about thermodynamics first. So I'm going to give a quick overview of the thermodynamic principles that I think are kind of governing the processes of change on this planet. So according to the second law of thermodynamics, the total entropy of an isolated system will always increase over time, resulting in a form of energetic stasis or death. So the universe, in some ways, through the Big Bang, is starting to die. And this is the change of entropy. The only matter that does not change in this way has already reached thermodynamic equilibrium. Everything else is changing. So another kind of change that counters this law is wielded by the material expressions that actively assert their thermodynamics difference from the surroundings. And they do this by spontaneously increasing material and complexity, seemingly working against entropy. And this is the change of synthesis. So this dance between thermodynamic entropy and thermodynamic synthesis is irreducibly complex, and it's a balancing act between change associated with active agencies. And to this time, we can only attribute those properties to the materiality of this planet, and it is most effectively demonstrated through the phenomena of life. So, to date, we have completely failed to totally decipher or exactly replicate this system of material processes and thermodynamic transfers. And so whilst no single process defines this conundrum, Earth's living communities collectively draw on the physical conditions associated with our planet to forge these cycles of life. So it's turning thermodynamics in on itself. It's able to do this because of the conditions in which we exist, with a relatively consistent gravitational field, a stable orbit, and abundant liquid water. So let us now go back to the story of the Earth. So around about 4.5 billion years ago, Earth collides with the impactor Theia and broke apart in a giant impact. This giant impact hypothesis is sometimes called the Big Splash, or the Theia impact, which resulted in clouds of molten debris and vapor that surrounded Earth, which coalesced to form the Moon. And this natural satellite is therefore made from a mixture of proto-Earth and Theia remnants. The collision also contributed to the mixing and redistribution of elements within the Earth's mantle, leaving behind two giant masses underneath Africa and the Pacific Ocean. So our planet is not a single planet, it is a conjoined union of two cosmic bodies. This results in a higher than usual iron content of the planet for its size, and that's caused by the additional material of Theia. And this means that it has a powerful magnetic field, which has also so far prevented the solar winds from sweeping away its gaseous atmosphere. And so after this violent birth of the Moon, I think it's just important to establish the extraordinary properties of our planet, so that we can no longer look at the material world as this kind of dead, passive entity, and really start to address the active forces that are continually turning the cycles of life. So after this violent birth of the moon, the Earth continued to undergo dramatic changes, bringing about the formation of tectonic plates, which themselves are also contributing to the shaping of the dynamic planet's surface, and they act kind of like magnetic stirrers. They're pushing and squeezing the surface of the Earth, enabling actually the minerals in the mantle to turn over, so that over time we get leakages of magnesium and then calcium, which also influence the processes of life. Over millions of years, we obviously get characteristic geological features due to the dynamic activity of the Earth, but also through the formation of oceans and a chemistry that really is not still. The idea that a non-still chemistry that takes agency through the form of life should not be a surprise for the materiality of this Earth. And I think through this ability to think through nature as a material actor, as a kind of planetary scale technology, rather than as a passive backdrop for human action, is really important. And so the nature of nature itself is forged. This is Latour's idea of the earthbound, that of living entities that are produced by and reside on a dynamic material platform. And I think this is really important to realise that the nature we know was, forged by the geotechnical system of the world, and through these constant movement of the planet, it materially feeds back into itself. And we can consider the chemical evolution that becomes a biochemical evolution to be influenced by a natural technology called metabolism, which is an active, sustained material exchange and transformation of matter between lively bodies. If we think about the origin of metabolism, it will first be a geotechnical metabolism and then a biotechnical metabolism as interfaces and boundaries are forged that promote the diversity and exchange of material species. The first of the, let's say, the named organisms that came after biogenesis that have profoundly affected the formation of the planet are the cyanobacteria. And they are simple. I think this is a modern prejudice. We call them simple forms of life, but they have persisted over 3.6 billion years or more to create the first kinds of cities on the planet. And not only do that, but by the byproduct of their own metabolism that transforms sunlight and reducing gases like carbon dioxide and methane into biomass and water, they have absolutely transformed the atmosphere. And so the importance of oxygen in the history of the world is just remarkably significant in the sense it made so many more chemical species possible, not just for life, but also for the rocks. And if we compare the mineral compositions of our planet with the other planets in the solar system, other planets will have about 500-600 mineral species, whilst we have over 2,500 mineral species. So life and rocks are evolving together. The material world is deeply entangled. And it's so interesting how we do not recognize the life of rocks when Linnaeus certainly did. But out of this planetary scale melting pot and kind of mixing system, the living world as we start to know it began to form. And although we have many different kinds of materialities that are contributing to the active agents that forge the living world that we recognize as nature, we have a human prejudice already in retrospect, trying to create, let's say, differences of significance between these bodies. And I think here that we really need to think about the difference in, let's call it a thermodynamic prejudice that we have, which is about life over the other kinds of material bodies on the world. And so from classical times, we have made a distinction between the bios and the zoe. The bios being entities that Agamben and others being entitled to a political existence, whilst zoe is referencing their life with limited civil rights. And with underneath that, we have mineral rights, which are almost not acknowledged at all, which leads to the privileges for mining and extractive behaviours without losing any of our say, we have no empathy for minerals, put it that way. And I think, kind of being blind to certain kinds of matter makes it possible for us to devitalize the living world without us being conscious that we are doing it. And I think at a time of planetary scale devitalization, the realm of bare life, zoe, and the mineral realm specifically demand a rethinking of how the living world is valued and related. I think for me, this is where a new mythos for life begins, which is the foundations on which life becomes possible. And so since modernity has transformed the Earth and the cosmos into a vast technological network where value is complicated by economic systems that profit from planetary damage, an emphasis on zoe is needed that is concordant with new materialist concerns, amongst many others, to consider things like agency, power, subject formation, ice sheets, and co-constitutive productions of reality. So this involves new kinds of actors in our story about change, which should involve soils and atmospheres, ice sheets, viruses, and all kinds of dynamic materialities that are not categorized as true life. And their depletions and deteriorations and accumulations are significantly impacting bios. Jane Bennett famously will refer to the garbage patch as an agentized force that is releasing different kinds of substances actively into the world. And so I think only by engaging these actors fully in ways that are compatible with performing work, one of the aspects of technology, but not limited to human concerns, can produce approaches, protocols, and paradigms for the design and innovation in human settlement to be realized in ways that potentially could promote planetary liveliness. So I think the framework that classical science has imposed on matter has allowed us the privilege of consumption. And yet Earth's matter is thermodynamically empowered, but we have learned how to regard it as inert, brute. So Newton reacted against that, and a mere standing reserve for human use and consumption. These Enlightenment concepts underpinning maternity characterize the classical laws that assert the material immutability of our world, whilst factoring out its inherent ingenuity. Of course, Heraclitus recognized that, but how do we actually implement the idea of a world perpetually in flow? And I think that this has become the goal of systems science, although I would argue that systems science is really descriptive rather than able to implement dynamic material engagement. And we still really have to think how we reduce things to building blocks of matter before we can start to think about how technological change can take place, so that everything still has to be reduced into basic elements. And I think that science has had an incredibly important role in helping us to better understand the dynamics of the world. And I think classical mechanics has provided a really interesting and robust framework for understanding the motion of macroscopic objects, the behavior of electromagnetic field, but it has gaps in its knowledge. Specifically, it does not explicitly incorporate the effects of the strong and weak nuclear forces and for forces like gravity. So how these forces are still crucial for understanding the behavior of particles at the atomic and subatomic levels, and classical mechanics cannot address this realm. So this leads us to the revolution in matter, the quantum mechanics, which we are really only starting to engage, but mostly still using a classical material framework. So quantum computing, you could argue, still has many of the tropes of Enlightenment materiality, but with a quantum layer. And I think a bit like how we started to build bridges out of steel. The first bridges in the Industrial Revolution were built with iron pieces that were fashioned like dovetail joints, which are characteristic of carpentry, which are native to materials like wood. And it was only later then that vast spanning bridges using the intrinsic properties of steel led to new kinds of design and engineering. So I still think that in terms of the quantum realm, we are starting to try to decipher what it actually means, because quite frankly, right now, we still don't fully understand it. And I think that that understanding is really limited to a classical understanding of matter, rather than kind of opening up new spaces for thinking about the entangled relations and the weirdness of this space. So I think the fragmentation and the strangeness that is counterintuitive, which characterize quantum mechanics, helps us better understand the peculiarity and the dynamic nature of macroscopic objects, which we have comfortably framed within the classical realm through the language of coherence, where essentially, if you have enough molecules stacked on each other, they start to behave in a way that we can describe in classical terms. But what that does is it also factors out the dynamic perspective of the material realm. So physicists like Ilya Prigogine were really looking at the thermodynamic principles of dynamic systems and came up with the idea of time's arrow, which refers to the tendency for physical and chemical systems to evolve towards states of increasing order or entropy. And this is where our kind of levels of awareness that maybe there are other ways of thinking about materiality which are more about having a judo throw rather than complete and utter control of the state of matter. So Prigogine's notion that time's arrow points in this direction towards towards entropy. It means that the asymmetry in natural processes moves systems from states of lower entropy or order towards states of higher entropy or disorder. And the directionality of time is specific to material events because it reflects the fundamental thermodynamic principle that natural processes move towards these states of maximum entropy. And so the classical example is about the mixing of gases or the diffusion of particles so that everything reaches a negotiated intermediate state. But Prigogine also noted the concept of the dissipative structure as an example of how, when driven by energy flow and dissipation, material order can self-organize from chaotic or disordered states. So the energies from dissipation, which is the giving out of energy from a system, can be fed back into themselves in the material realm. And this is typically formed within far from equilibrium systems, including things like convection cells, chemical oscillators, and even living organisms. And these material agents seem to become stable, coherent entities that persist through time, through a process that Jeremy England called dissipative adaptation. So Erwin Schrödinger was also really interested in this weird space, and he observed that some materials resisted the decay towards increasing entropy and termed this phenomenon negative entropy or negentropy, the idea of order from disorder. And specifically, he noted that living organisms maintained their internal order and complexity by continually exchanging energy and matter with the surroundings via a range of material strategies, including genetics. That was his particular interest, that was Schrödinger's interest, with the DNA, which he thought was a periodic crystal. And so these kinds of geometric answers were given to these processes of dynamic flow. And this really provided a new view of nature as an organizing force that could work in conjunction with physics to create a different kind of state of matter in the process of dynamic, structured dynamic change. If we go forward again, sorry, just not a Mac pattern. I'm going the wrong way now. There we go. Try that one. Where are we there? Yeah, so so essentially we get an idea of empowered matter, particularly at the thresholds of equilibrium, at the point where non-equilibrium dynamics occur. And essentially, not only do these systems become ordered through the energy and matter they feed back into themselves, but they also become patterned. And in 2010, with the celebration of Alan Turing's centenary, the idea of natural computing started to be discussed, where the idea of dynamic systems, material systems, could compute. In other words, they could make decisions about their state and in relationship to their surroundings. And so there are a number of different scientific practices that have evolved. Some are called morphological computing. They come from the field of engineering, and some of those are called unconventional computing, and those are more related to biology and chemical systems, such as this Belousov-Zhabotinsky reaction, which is an oxidation reduction process that results in the transfer of an electron through different, let's call it substances, creating color change, and it forms an incredible, almost like a fractal-like dynamic pattern. So the possibility, and of course these can be disrupted, which adds to the computational nature of these systems. In other words, it's very basic material decision-making processes. And so within these potent fields of activity, excitable molecules away from equilibrium states can renegotiate their configuration, spatial distribution in relationship to others via fundamental chemical properties that leverage the opportunities presented by probabilistic systems. And with repetitions within lively systems, bifurcations are created that require matter to make decisions at these points and act upon it. And this agentized matter is not considered fully alive, but it is a fundamental characteristic of Zoe, and in deep time it is also a characteristic of the mineral realm. So whilst the origin of life is usually recognized as the starting point for the transition from non-living to lively and finally living matter, it is bios rather than Zoe that we give a center stage to start to valorize our engagement with a dynamic planet. And so to explore the potential of how we might actually use these dissipative structures, how we might start to think about a 21st century meeting of physics, biology, and chemistry, I started to create instruments, let's say agents, that I could interrogate much more like a fortune teller than a scientist, because it is just very hard to empiricize these things. And so I wondered how it may be possible for self-fulfilling organizing chemistries to build a city from the bottom up. And if we look at the origin of life, and if we listen to Darwin's, warm little pond, and if we look at some of the more contemporary theories about how life's origins maybe came from black ventas, the smoky hydrothermic vents at the bottom of the ocean, you actually really need water for a dynamic materiality to help start organize itself. And even as biological bodies inside of us, as William Bryant Logan says, we contain our own seas. So we bring our own water onto the land with us. So I started to look at a city that had an interface with the water, and I was looking at the foundations of the city of Venice as a starting point to think about how we might start to grow instead of just preventing like King Canute, the advance of the sea. Could we empower the city itself to resist the change in ways that are conducive with humans? So the city is already doing this through an incrustation of layers of different organisms, from oysters to algae to thrombolites, which are kind of like stony aggregates of bacteria on the side of the waterways. But could we do this in a way that would have a negotiation with human settlement? So I developed, or I started to work with a technology that was last described at the end of the 19th century by Otto Büchli. It's called the Büchli droplet. Otto Büchli was a Swiss zoologist who comes out of a tradition of scientists who had devitalized matter and considered biology as a more complex expression of synthetic chemistry. So that all starts with Wohler and his synthesis of urea from inorganic matter. So the adage of the alchemist was that, life was special and it had a special juice that made it living. And in the 19th century, scientists were taking that theory and testing it through chemical synthesis. And so this idea of chemical synthesis and synthetic chemistry came about. But Otto Büchli was using this idea of chemical synthesis to create organisms. So again, with people like Moritz Traub, who said he made the first artificial plant, Otto Büchli was actually looking at how we would, I'll go back a slide and come forward again so I can talk you through this weird and wonderful process. So Otto Büchli said that if you add potash to olive oil, you could actually get a very simple organism, or protist it was then called. I'm really not a PC person. And here we go. There we are. So what you're looking at here is because it was 1894, Büchli had only done drawings, so I decided to look at Büchli's process under the light microscope at ×40 magnification, which means all those little white dots you're seeing are about 1 millimeter in diameter. What I did was I used extra virgin olive oil as the background, so all the black is extra virgin olive oil. Don't use the light version because they've got things added to it that makes the background less lively. And the white dots are actually sodium hydroxide rather than potassium hydroxide, which is the potash that Otto Büchli used. So when the spot of alkali breaks up in the oil field, it makes soap. Right? So what you're looking at is an alkali droplet that is making soap on its on the outer aspects of its body. But the weird thing is that it created these kinds of complex formations, not only in terms of their morphology, but also in terms of their behavior. So just very simple molecules, sodium hydroxide plus olive oil, oleic acid, if you like, can actually create complex dynamic morphologies, which I started to plot. And these are a function of chemistry, and also the stability of the interface between the oil and the water. So through instabilities and over time, these bodies could transform into various kinds of active matter. And so I started to figure out how I could influence these. So for example, these bodies love alcohol because alcohol changes the surface tension of the droplets. And honestly, you'd think that these were kind of culturally sensitive because all those little droplets would migrate in a flash towards a drop of alcohol in the medium. But they would become extremely lively, and then they would fall into a deep coma and die. So you kind of got these kind of sedimentations of droplets rushing towards ethanol. But other things could also influence bodies, so different ions in the solution could also influence them. If you put calcium ions in the medium, they started to make mineralized traces. So I decided that I would try to re-articulate this in the context of Venice. These are thrombolites that are sitting on the canals of Venice, which are already doing this through a kind of bacterial metabolism. And so the idea was here really that the rate limiting factor in the Venetian waterways for biology is the availability of calcium, because it's a very dilute molecule. Everything loves calcium, and it dissociates from its bonds very quickly with changes in pH, and therefore it's good for building bones, but it's also good for dissolving bones. So the amount of calcium is the rate limiting factor. So the idea was that if we added protocells, gave them a metabolism that made them go away from light, we could send them towards the darkened foundations of Venice, where oysters don't need light in order to metabolize. They just need some dirt and some water. And then they could build up shells. So the idea is a kind of a reef-like mineralization by simply kind of trying to choreograph dynamic matter in the vicinity of a city to try to thicken the foundations and prevent the rotting of the wooden piles underneath the city that are there historically, which are getting more exposed by the passage of the Grand Navy, the big ships. So essentially the idea then that we could work synergistically maybe with the wildlife by essentially it's a persuasion molecule, the calcium, is there a way really then that we can start to use these principles to create a technological platform that isn't just nature's to use, but to one which we can start to influence and engage with. I won't talk about the politics of that because it'll be very complicated, but I'm really trying to think about the platform through which we can really start to talk with the smallest agents of the planet so that we can really start to think of mobilizing matter, mobilizing change from the bottom up. And so whilst dissipative structures create further opportunities to resist entropy through this continual flow, choreographed flow of matter, we really need to start to think about how we can develop production platforms that take these metabolic systems further. So the idea then was these protocells, these chemical bodies were very temporary. They quickly reach equilibrium, ranging from a couple of seconds to just over an hour, but not longer. But microbes already are able to work with this kind of level of chemical stitching. And so what I've been doing is really starting to use microbes as the basis of a productive, versatile system that can underpin, let's say, a culture of human development that works along with the processes of nature, not as a form of copying, but actually as a way of channeling life and the structures of life into the spaces that we inhabit and other spaces too. Essentially, the 21st century has brought us insights into the living world of microbes and how they have formed, how they have been able to form cities themselves. These may not look as beautiful as Belgrade, but they are incredibly organized. Interestingly, in microbial cities, biofilms, the living elements are on the outside, and then you build on, or they build on the mineralized remnants of the dead. So these are, you're like looking at mineralized graveyards of microbes underpinning a kind of a rock-like structure with a living city living over the top. This is in Australia, it's Shark Bay, and these are called stromatolites. So essentially, from the protocell experiments, I've been trying to choreograph microbes through bioreactors, which you could think of as being houses for microbes, start to bring them into a domestic space as an ecos, as an economy for exchange of matter as a kind of valued resource. If we go back to the Greek ecos, the ecos is the system of economy. The marketplace is a supplement. So is there a way of empowering people through, this is just a rendering of a project that I was coordinator for the Horizon Europe pathways called Living Architecture, which started to incorporate these bioreactors within modern buildings, really to fundamentally replace our infrastructure, our utilities. Our utilities serve machines, not life. So can we bring microbes, can we bring circular systems into our living spaces? When we do this, we can see we actually need a lot more water. As I said, we contain our own oceans. If we want cities and buildings that are actually able to recycle our wastes and turn them into vital products, then we need to be able to figure out how we bring water into our living spaces. And specifically, we need very smart plumbing, because our plumbing is just dumb. And there's not enough of it, and we don't know where the leaks are, and so we have an urgent need. We need an infrastructure that enables us to really be able to process water, to return water, and with it all the metabolites of life. This is an installation, how long have I got, that is like a proto apartment that has a kind of a living system. I'll just race through. These are just examples now. I'll just shout out the titles. These are the kind of metabolic systems, the design for the system. This is another project called Active Living Infrastructure Controlled Environment, which is actually a microbial cyborg. So you've got iPads that are powered by dirt in things called microbial fuel cells, which are 15 kind of stomachs that are sitting there. So they're metabolizing urine, essentially, and turning that into electricity. This is a standalone entity that is not plugged in, that was at the Victoria and Albert Museum. And what we were trying to do, really, is show a language of microbes conducive with digital systems that make microbes more palatable and relatable as a technological system, because biofilms are something that you just want to reach for the bleach for. And this is my latest project here, which is microbial hydroponics, which is really adding complexity to the system by also wrapping the microbes around the roots of plants to try to generate nutrient-rich resource for plants from our waste water to make plants that are more tasty from hydroponics, bringing in all those microbial reactions that you get from the soils. And so this is an ongoing project which is going to create a little black box called a prosthetic rhizosphere. So we're kind of creating microbial communities to really start to, I guess, bring together in a more, kind of, we can't throw away modern technology, but can we actually start to rethink the relationship between zoe and bios, the basic chemical reactions that underpin our living world, the microbial reactions, but also the mineral needs like the fertilizers for our the plants that we eat. And so I think the exploratory mythos, I haven't really developed it. It's really trying to reposition the things that we know, so that it's not just fantasy, but there are things that science and, kind of many other disciplines have helped us appreciate over the last century. And we kind of need we need to think and really consider what the discoveries that we've had in the 20th century can tell us about how we might move forward differently in the 21st century through a cosmopolitics for all those lively materialities whose collective destinies are entwined with the liveliness of our planet. And essentially, I think the most important thing for me here really is this is a sketch. I mean, it's about that much of a sketch as well, and more people being interested in a mythos of matter, I think will give us some tools to help us deal with change in a better way. And whilst entropy's advance can't be halted, its arrival can be delayed. I think that humanity can help play the role of a trickster. I don't think this is about being a god or a rule taker. I think we can help do what we didn't do in the Industrial Revolution, which is complete the circle of life. Try to turn the system of life in a way going back on itself to avoid that entropic decay. So in some ways we might think of life as the engine for the 21st century, or the system for the 21st century, that can really help us innovate and create material surprises by better understanding dynamic resource and energy flows. For that we need, languages and imaginaries and kind of a rebellious attitude towards matter, grounded in a kind of accessibility through a technological or other platform, so that collectively, not only can we resist the material decay towards equilibrium, that we can also kind of take restock of our thoughts about our role at this intriguing and worrying time. So I'll stop there.